Okay, so now we start to talk about electromagnetic circuits, right? So before we are doing new sections, let's have a brief revisions on what we have learned in last lectures, which is very important for us to understanding today's new sections. Okay, so as a matter of fact, in last lectures, the first issues we learned is that so when there is a current, so that current produces magnetic field surrounding it. So these are the first concepts we learn. And then if we using a wires, carrying a current, make it into a coils like this, and we show here, then we can produce strong magnetic field inside the coils in a directions like this. So the relationship between the directions of the current of the magnetic field can be determined using the right-hand screw rules, as we show here. So anyway, in one word, that is, current produce magnetic field. The second concepts we learn about the magnetic force. Since that the current can produce magnetic field, and we know that two magnetic field intact with charges produce mechanical force between them. As a result, if we have a conductor, as we show here, that carry a current I, then it has magnetic field produced surrounding the current I. Surrounding current I. So if we put this conductor carrying current into a magnetic field B, existing magnetic field B, then the conductors and the magnetic field B may interact to produce a mechanical force. This mechanical force acts on the conductors carrying currents. So the values of the force is the products of the magnetic field B, the current I, and the physical size or the length of the conductors. So here, so another important parameter is the direction angles between the currents and the magnetic field. So by talking about these force issues, we introduced to you about the cross products. So the magnetic field is a vector. That means it has magnitude, it has a direction. The current also has the flowing directions, has the magnitude. And the conductor, of course, pointed to a certain directions. So here is the cross products, which when their angles be 90 degrees, their products be maximum. When their angles be 0 degrees, their products be 0. So that's the sign, angles between them. Also, we say cross products. Where they're crossed, they are the maximum force. So this is the formulas explains the force produced by a conductor carrying current put into a magnetic field with their angle difference. So their force directions can be determined using the left-hand rules as we show here. So that's the magnetic force. The second point. The third point is inductions. So if we put a conductor into a magnetic field, and if there is a relative changing between the conductors and magnetic field, then there is induced voltage on the conductors. So things, right, find out that, okay, so the induced voltage on the conductors tends to set up a new current that, okay, oppose, right, opposite to the motions, okay, or to resist the change of the flux responsible for the inductions of it. Okay, that's, okay, the meanings of the sign here. So here, suppose we have okay, magnetic flux phi, and we have coilers that have turn numbers n. We put these coilers in this magnetic flux phi, right? If there are some changes of the flux linkage to the coilers, okay, there are some changes, okay, the change in time, changing rate, changes of the flux linkage to the turn, okay, to the coilers, then there is a induced voltage on the coilers. The sign negative here states that the induced voltage against the original change, okay, original, right, currents changing. Okay, so because we can use in the current produce a magnetic field, and the magnetic field produced by the current, if there is changing, then there is induced voltage on the coilers. Okay, so this is the third concept we learned. Because this, we can imagine that the coilers in an electric circuit may affect the voltage and current issues if there are changes. Okay. So then, according to the inductions, according to the current produced magnetic fields, that we can, okay, have a so-called Faraday's laws, which is for the electromagnetic circuit. Look at here. Suppose we have a source voltage V that changing with times. Okay, changing with times. The voltage changing with times. And in a circuit, we have resistance R. Meanwhile, we have additional coilers, like here, coilers. If we have a current goes out from the source V, go through the conductor's resistance R, and go into the coilers, and produce magnetic field inside the coilers. If the current itself is changing with times, then the magnetic field produced inside the coilers also changing with times. When there is a changing of the magnetic field inside the coilers, there is inductions on the coilers. Okay, so these inductions on the coilers against the change of the voltage, source voltage here, against the change of the original current on the coilers. As a result, we can have a complete Ohm's law that includes the resistive voltage drops Ri and the inductive voltage drops d phi dt. Okay, d phi dt. So this is the electromagnetic circuit. Okay, so now you know the relationship between the electricity and magnetic circuit. Electrical circuit, magnetic circuit, electromagnetic circuit. So the linkage between the electric circuit and magnetic circuit is the induction terms d phi dt, which has been defined by the names. Okay, so let's know. So this is the Faraday's law, inductions. Remember, in the world now, all the conductors has a resistance. So if you have an electric circuit, there should be a source, that is the V represented here, a resistance that represents the power consumption part, R. If you have current flows on the conductors, whatever conductors, if you have current flow, there is magnetic field produced surrounding the current. So the magnetic field may be stronger, may be weak, depends on the conductor's physical shape, conductor's physical size. Okay, a typical one is the coilers, that which can produce strong magnetic field. But for general purpose conductors, even a straight line, there is magnetic field produced around it. So there is inductions. No matter whatever conductors, if there is current on it and the current changes, then there is inductions. That's it. So this is the general voltage equations. This is general voltage equations for all electric circuit. For all electric circuit, the complete induction, is like this. For DC circuit, because the voltage and current not change with times, so this term disappears. Okay, so for DC circuit, because there is no change against the times of the current and voltage, so there is no change of the magnetic field linkage to the coilers. So this term disappears. So that's why we have the Ohm's law, just like these two terms. Okay, so now the thing is that how much flux be produced by a given current, and how does the current change with the times? So that's the task of the analysis of this part of the circuit. It is the voltage V that determines the directions of the current. Okay. Okay, so this chapter's focus is to analyze this magnetic circuit. So this part is these elements, right? So if we have current applied to it, so we have magnetic produced here. So how strong the magnetic field is, what is the effective induction functions of these coilers? That's the that's the case of it. Remember, so far, because we talk about DC, so there is so-called current directions. As a matter of fact, in practice, in most cases, we use the AC, that where the polarities of the voltage changing against times, positive, negative change. As a result, the current also change, positive, negative. Okay, so in the circuit, the current and voltage, it is the voltage, source voltage that determine together with the impedance that determine the current directions, which we will started in detail in the chapter 3. And this moment, remember the source voltage determine the directions of the currents. Okay, now, so that's what we learned, and then to analyze for so okay, so for analysis of the magnetic circuit we just mentioned, so we introduced the following concepts for convenience of analysis of the magnetic circuit. The first thing is that the magnetomotive force, because the current on the coils produce the magnetic field, so the current on the coils serves as the source of the magnetic circuit. Just like the voltage in electric circuit serves as the electric current source. Here, the current on the coils serves as the magnetic field source. So the current I on the coils N, the coil turn numbers N, okay? A straight line can be considered as turn numbers 1, right? So the current I with coils have a turn numbers N serves as the magnetomotive force, which to produce magnetic field in the coils. Okay, so which we use in the symbol F here represented. But this F is different from the mechanical force F. This is the magnetomotive force. Okay, so now using this magnetomotive force to produce magnetic field inside the coils. So the magnetic field, okay, magnetic flux inside the coils proportional to the magnetomotive force of the coils and over a so-called reluctance. So the reluctance here represents the capabilities of the coils to allow the flux, magnetic flux, go through it. We can imagine what factors affect the flow of the magnetic flux in the coils. The first thing is that the cross-sectional area of the coils, okay, if the coils, okay, cross-sectional area is bigger, then we have bigger rooms to allow the flux go through it. Just like the river, the wider of the river, the easier of the water flow through it. So we have cross-sectional areas. Now, the second factor is that the longer of the coils, the more difficult for the magnetic flux goes through the coils. So the length, if the coils length is very longer, that the route is long. Okay, so the flux is difficult to go through these coils. Okay, one more parameters is the so-called magnetic permeabilities, which is a unique concept to describe the material's natures. Okay, so because the coils can be made on different materials in the airs, on plastic coils, on steel cast materials, on copper materials, on whatever materials. So each materials has its own properties. So in terms of the magnetic field flowing. So some materials allow the magnetic field flow through it easily. Some of the materials making the magnetic flux flowing in it difficult. So we introduce magnetic permeabilities. The larger of the permeabilities, the easier of the magnetic flux to produce inside. The smaller of the permeabilities, the more difficult to produce strong magnetic field in it. Therefore, we have reluctance for a given coils that depends on the physical parameters of the coils material. L, the length of the coils. A, the cross-sectional area of the coil path, or we say the core materials cross-sectional area. And mu is the permeabilities of the core materials in the coils. Okay, so once again, the mu here represent, right, the core materials inside the coils. Okay, so the larger of the permeability, the stronger of the magnetic field produced inside the coils for the same currents. Okay, with the same current. Okay, look at here. So we produce flux here. So if the current no change, the smaller of the reluctance, the stronger of the flux inside. And for the reluctance, the bigger of probabilities of smaller of the reluctance, smaller of the reluctance, stronger of the field here. So look at here. So the probabilities mu here very similar to the conductivities in the electric circuit. Okay, and the reluctance very similar to the resistance in the electric circuit. In the electric circuit, for a given voltage, smaller of the resistance, bigger of the current. For the magnetic circuit, for a given magnetomotive force F, or we say for the given currents, the smaller of the reluctance, the bigger of the flux. So the flux very similar to that of the current in the electric circuit. So the phi equal to F over S, very similar to the Ohm's law in the DC circuit. All the rules applicable to the Ohm's law is also applicable to the phi equal to F over S. Hope you get to the point. That we learned many rules that can be used to analyze the Ohm's law. All rules can be applicable to the rules we learned for the phi, F, and S. Okay, so if you so forgot this one, you can review the records later on. Okay, to study. Okay, so and today, so we can introduce for the Faraday's law. We can furthermore to introduce so the inductance to represent the relationship between the inductions and the current in a circuit, in a circuit. Here say we a circuit, this electromagnetic circuit. So this is the magnetic circuit parts. So if we have a coils, this coils is applied with a source voltage V and result in a current I flow on it. So if the coils has a resistance R, then so and if the current on the coils changing with times, then we have an inductance d phi over dl. The phi, as we just defined, which is the turn numbers times the flux produced inside the coils. And we can write further to define that the flux phi, that is the okay. So the total flux linked to the coils originally is the turn numbers of coils times the flux inside the coils. And you know that the flux that actually produced by the currents on the coils, so it can further be linked to the current with a constant L. So based on these definitions, one can find out for a given coils with a current I how much flux linkage to produce. Okay, so the L is the flux linkage produced by 1 amperes on a given coils. Okay, that's the definition of the coils. So this is definition of it. Okay, so L is being defined as the inductance of the coils. For a given simple coils, okay, so then based on this definition as the Phi's definition, okay, so based on the linkage, right, definitions and inductance, based on the phi that depends on the magnetomotive force over reluctance, and reluctance related to the physical parameters of the coils, so L mu A, and the magnetomotive force, which is the turn numbers N times the current I on it. So one can easily gauge the relationships between the inductance and the coil's physical parameters. So that's why we have an N square, right? N square here. Because you have N here, you have N here, N square here. So one N represents the producer. Another N represents the one accept the flux. So the F equal to N, the N here means that this coil produces magnetic field. This N means that this coil itself accepts the coil's flux. So produce, accept inductions. This we call it self-inductions. Hmm? Okay. So because that time we were talking the other inductions, so here we get, by the way, to telling you the clearly, the meanings here. So as you see here that we have two names, N squares. So one N represents the producer, so the field producer. The other N represents the field, right, inductor. So here the magnetic field producer and the voltage inductor, the same. They are the same things. So self-induction. So self-inductions. Okay, so the inductance here is the self-inductance of the coils. Imagine it is possible that we put these coils into another magnetic field produced by another coils, right? Okay, just like you, right? So we can produce by ourselves, okay, the voice, and our ears is in our self's voice. That's self listening. Okay, you also can listen to the other people's talking. That is talking to the others, okay, making your calls, right? Okay, so the same things. Okay, here we have the self inductance. Remember this one, and so for any simple coils, we can use these formulas to do the right calculations to estimate it. For a complete one, using this one. Okay. Okay. Now, one more thing is that because later on many students okay, using the wrong issues, wrong formulas to deal with some of complicated cases. So as I said, for any simple coils, you can use in this one to estimate the inductance. But for general case, okay, for complicated coil circuit, you should use in the original definition of the coils, that is L equal to phi over I. Furthermore, is the length square of the source coils over the circuit reluctance. So N is the source coils that taking current, and S is the reluctance of the total magnetic circuit. Remember this one. Remember this one. Okay. So now we have to learn how to analyze a magnetic circuit based on we have learned about the magnetic circuit concepts, right? So in practice, we have many applications of the inductions. One is the so-called current transformers. Here, just to give you one example, that suppose we have wires, that on the wires we have current I, then we have magnetic circuit produced surrounding the I. You can using the right hand rules, so the thumb point to the current directions, and your four fingers point to the surrounding magnetic field directions. So you have magnetic field directions. Then, so you have magnetic field like this. If you have coils, as we show here, ring coils, which what we draw here is the core. This is the core, ring core. Generally, so we have a ring cast steel core. Okay, this is a ring cast steel core, which has a very big permeabilities. And on the core, we have a few coils. Okay, so the core is very big, but on the core we can make in one turn, two turn, three turn, and turn. Okay, according to needs, right? Demands. Okay, so then because the current on the wires in practice for AC is changing with times, so their induced voltage on the coils here, so the voltage also changing with times. The voltage changes with times. So the stronger of the current on the wires, the bigger of the voltage induced here. So we're using the induced voltage here to produce another current. So this current can be measured. Suppose that on wires we have 1000 amperes current. We can induce 1 amperes current on the coils here. So we have 1000 to 1 ratios. Okay, just an example. So that's the current transformer. Okay, current transformer. So we can use a small ammeters monitor 1 amperes. When we got 1 amperes on the monitors, we say, oh, the wires has 1000 amperes because you cannot direct measure the 1000 amperes. Okay, so that's the current transformers. Not just for the current transformer for the measurements, but also sometimes we use the current transformer for protections. So CT for measurements with higher accuracy. CT for protection uses. Okay, now here, so why we learn about CT here? So we just telling you the CT's, okay, CT's right principle, okay, which is based on the inductions because the wire produce magnetic field surrounding it, okay. So we can using these principles, okay, to make a CT, make CT. So in practice, CT has two purposes. One is that for the measurements. So generally, for measurements, we should have a very high accuracy because you want to measure the current on the wires. So another purpose is that we use the CT for protection devices. So which you will learn in next year. So the power distribution. On a power distribution, you frequently use the CT for at different parts of the power distribution line. Okay, so for protection purpose. So we detect how much the current on the systems. Then we determine whether switch on or switch off or short circuit, open circuit the circuit, okay, using the CT devices. So CT devices is a very, very useful devices in electricity usage. Okay, remember the one? Do not say that you didn't learn about the CT, okay, when you study about the power distribution subject. That's the CT, okay? Now, we go ahead to learn how to draw a magnetic circuit using the concept of the magnetomotive force F, the flux phi, and reluctance S. Okay, now we're using one simple coilers to showing you how to draw the magnetic circuit. Here is the previous coilers we showed to you, which has the course length L, okay, which has cross-sectional area. Okay, so here, so the coil's length is, as I show here, is L, right? Coil length. And the cross-sectional area is 1 turns ring, okay? 1 turns, okay? This is a ring, 1 turns, just like your figure ring, okay? So the cross-sectional area A. And what's the meaning of the phi? The phi here is the total flux lines here, total flux line here. Okay, so let me further to explain the parameters. So the L is the coil length, the path length. Okay, the phi is the total flux, magnetic flux lines produced by these coils, and the A is the core cross area. Here the core is air core, so air core, right? Inductor core. Then we have the magnetomotive force, produced by the current on the coils, which is the magnetomotive force, which we use in the F to represent it, and which is the product of the turn numbers of coils and the current on the coils in I. And then we produce flux goes throughout the coils in the space, in the space, in the air, which we have the total flux here. So the total flux then goes from the north pole. So this is the north pole. Okay, go out from north pole and the south pole. Okay, so go out from north pole and in the air, that back to the south pole. So imagine that magnetic spread in the air anywhere. The magnetic field can spread in the air anywhere. Just like the Earth, we have magnetic field in the space, which start from the North Pole, to South Pole. So its path very high, goes into 3,300 meters, 300 kilometers to 1,000 kilometers high, and then return to Earth. Okay, so the path of the magnetic field is a very, very long and large one. Okay, so here, so we just can use the concept of the equivalent path reluctance. Okay, then we suppose the coils has a equivalent path, a reluctance. And we can see the flux here. We have 2 parts. One is the flux inside the coils, which is for inductions. The other part that leaked into the air through the gaps between the coils. So as you see here, This is the leakage, right, flux. So we have the leakage flux. We have the useful flux. We call it magnetizing flux. So leakage flux, magnetizing flux together plus together is the total flux. So they are in parallel branch, just like a currents, right, in parallel branch. This is the total flow, okay, current, flux flow, current flow. This is the leakage flow. This is the useful flow of the flux. Okay, they are in parallel. And corresponding to the leakage flux, we have the so-called leakage reluctance. Okay, so we have so-called SL, that is leakage reluctance. So generally, the leakage reluctance for a coilus is very small. Okay, if the coilus close touched together, then the leakage here will be very small. Okay, very small. Particularly when we're using a core here. So leakage reluctance, because the large leakage reluctance, okay, so generally the leakage reluctance is large. It's large because we don't like to leak more flux in the air, and the magnetizing reluctance is small. So we have much more flux goes through or inside the coilus. So this is the magnetizing reluctance. That is the coilus magnetizing reluctance. This is the simple equivalent magnetic circuit. In most of the cases, if the leakage is small, then this can be thin, open. Okay, not always. If the leakage reluctance is very big, then this branch can be thin, opened, thin, opened. And the useful branch. So you have the source, you have the flux, you have the reluctance. Their relationship is phi equal to F over X. Okay, so that's a simple flux, magnetic circuit. You can use the Ohm's law to solve such a circuit. Imagine that F is the voltage, phi is the current, and S is the resistance. Okay, Okay, so for your memory, I write down these issues. Now imagine that the F magnetic force is like the voltage V, and flux phi is similar to the current, and the reluctance is similar to the resistance R. Then you can use in the ohms, right? The way of the ohms law to analyze the magnetic circuit. Okay, because and then they may have students still asking me about how to deal with parallel branch, how to deal with the series branch, how to deal with two coils in series, and so on. Many similar questions will appear. But once again, so you can use in the laws you learn for the electric circuit, to analyze the magnetic circuit. The only thing is that imagine that the magnetic force F is the voltage, the flux is the current, and the reluctance the resistance. Using such a way to it. Now, so this is important issues. Another point is that the difference between air-cooled coils and non-air-cooled coils. So currently, what we show here is the air-cooled coils. There is no metal cores, or we using the non-magnetic forms of plastics, or no formers. That means we no cores. So such a coils has a very big reluctance because their permeability mu is small, which is the free space 1 mu 0. As a result, the reluctance is bigger, the inductance is smaller. So inductance values does not vary with current, which is a constant, which is low values, which is suitable to application to the high frequencies, because that's the channel rate. Channel rate. Induction, because of the induction. This is inductions. This is the inductance. So imagine that if the di dt, that is change rate, is very, very high, and the inductance is very big, then what happened? The induction was very big, right? That is terrible. So that's why in the high frequency instruments, we're using a small and a constant inductance. That's the meaning of it. Disadvantage is that it has a relatively big leakage because you have no cores. So the flux may spread in the air. So big leakage of it. So that's the advantage and disadvantage of the air-cooled coils. So anyway, from this slide, you should learn how to draw a magnetic circuit for a given coils. Imagine that the magnetic force, like the voltage, the reluctance, like the resistance, the flux phi, like the current. Then you can use in the Kirchhoff voltage law, Kirchhoff current law, the Ohm's law that we used for the inner circuit to analyze the magnetic circuit. So in practice, in many cases, we're using the ring coils. That is the toroidal coils, like this. We're using a core, ring core, toroidal core, and a wheeling. So the turns, we manipulate turns on it. So they turn together, we call it wheelings, wheeling, or coil. So core, coils, because some students, always confused with this one. Which equivalent to a infinite long coil, small leakage flux, linear circuit issues. Okay, so because the magnetic field produced by the coils or by the windings is inside the coils on the cores. There is very small leakage, okay, very small leakage, particularly if the coils, right, is closely touched together to each other. If you have several layers of the coils on the core, not just one layer, okay? So one layer on the core, you have another layer, or 3 layers, or 4 layers. Maybe someone always open some of the chargers or transformers, okay, that are used, right? So you think that. So when you're looking at the inside of a small transformers, you found that there are thousand turns of the coils wood on a small core. So there are many layers, not one layers, many layers. So in that case, they almost has no leakage. That's the meaning of it. Okay, so permeability issues. The core materials may be a plastic core, may be a wood core, may be the air, may be a magnetic materials. Okay, so each materials has its own permeabilities. So suppose we apply the same magnetizing force or magnetizing strength or magnetic field strength, magnetomotive force over legs. Okay, or we say the turn numbers Ni over the length L. This is the L, right? Length. Okay, so here we have a new concept of the H, right? So the H, we call it magnetizing force, or we call it magnetic field strength, or magnetizing force. So physically, it means that the magnetomotive force over per meters, okay, long of the coils. So of the turn numbers N times I over length of the coils, that is strength. That is strength. Okay, so you have the magnetic strength, but how much flux produced depends on the permeabilities of the materials. That's this one. Okay, so for a given magnetizing strength, for a given magnetic field strength, depends on the permeabilities of the core materials, okay, you have magnetic flux densities produced. Okay, so the relationship between the magnetic flux density B to the magnetic field strength H is B equal to mu times H. So the mu is defined as okay. Okay, so this is the relation between B and right H here. So you now understanding the meanings of permeabilities. Okay, so you apply the same strength of the magnetic field into the coils. Because the material is different, the magnetic flux produced inside the coils will be different. That's it. Generally, in the air, the permeability is mu0. And any materials, the permeability can be referred to the air permeabilities by introduce a relative permeability mu_r. Okay, so this is the total permeabilities, which is the relative permeability mu_r times the absolute permeability mu0. Okay, therefore, for a given materials, that permeabilities is the ratio between the H over the B. Now, some students may ask, in practice, how to monitor the ratio between H over B. Now, telling you one practical experimental method. So you know the H is due to the current applied. So the strength of the magnetizing strength depends on the current applied. No, mu equal to B. Oh, yes, you're right. Okay, you're right. Okay, so thank you, the students, right? So sometimes I make mistakes, right? We're drawing some things, okay? Okay, so the mu, therefore the mu is the B over H, right? Mu over H. So in practice, the mu be obtained by experiments. How to get the mu in practice? So we can apply a current given a coilus. So we can apply a current given the coilus. Apply the currents given coilus. So the current, the numbers together represent the strength of the edge. Am I right? Okay. And then we can monitor how much magnetic field induced. So the magnetic field can be measured with the induced voltage. So the voltage currents, we can monitor, okay, the applied currents and the induced voltage on it. Okay, across a given coilus by using an oscilloscope. So therefore, in practice, you have the oscilloscope, sorry. Okay, so you may have pH curve. So for a given materials, you can apply the current that is H. You can monitor the voltage induced across the coilus. That's the B. Okay, that's what I write here. And then you got a pH curve. From the pH curve, you can obtain the permeabilities. Okay, so you can measure the permeabilities in different materials with different current values. You can carry out experiments to obtain the pH curve, therefore to obtain the permeabilities. So you will find that the permeabilities mu may change with the currents. That's the non-linearities. So in practice, in the DC case, right, no such problems because DC the current no change, right, and all. In the AC, this is the big issues of it. Okay, so that's the relation between the mu, B, and H. Mu, B, and H. So far, okay, there we learned about how to experimentally obtain the pH. Okay, so here is a summary about the air-cooled coilus. Okay. Therefore, right, toroidal air-cooled coilus, not for the other type, right, called air coilus. So we can simply using this one to do the calculations. So if you have turn numbers N, you have the current I, and then the magnetic motive force F can be represented, right, using this one, and the magnetizing field strength, magnetic field strength H can be estimated using the turn numbers current I over the length of the coilus, because the coilus is a ring coilus, and a mean flux density, mean flux densities, which can be estimated. So the flux produced over the A and the B and H relationship okay, be the mu 0. Okay, because if you know the H, okay, mu 0, the B can be obtained, and then the flux can be obtained. And also that's the reluctance, okay, the other okay, parameters, including the reluctance, including the inductance, and so on. Okay. So here is the examples that we conducted okay, in the tutorial sessions on Tuesday. We already talked about it. Okay, so that's based on the air-cooled coilers. Okay, which there we analyzed in details about the coilers. Okay. So here is just showing you again about that. Okay, which you can compare with the contents we just learned to understand again what we did for these examples. In practice, we also have the air-cooled coilers. Air-cooled coilers, you look at here, because we have the air core. Therefore, the structures much more complicated. Looking at here, suppose we have a EI type, okay, ferrous core coilers like this, and it has two parts of the core. One is the type like E. The other one is the part like I. So if in the center branch, if we have 100 turns of the coilers wood on the center, if we apply the current on the coilers here, then they produce magnetic field on the coilers. The magnetic field produced on the central part will goes out and separate into two branches. One is the upper E leg. The other one is the lower E leg. Once there is a magnetic field, this magnetic field will attract the I part to attach to the E parts, form a closed ring, okay, a closed core. Okay. So now, if you apply another mechanical force on the I parts, for example, you have a spring. Okay. Okay. Sorry. So we can Okay, so in practice, so we can using a mechanical force from a spring to pull the I part away from the E part. Okay, part away from the E part. And on the other side, so a magnetic force from the E part to pull the I part close to the E part. Okay, the stronger of the current, the bigger of the magnetic force. The smaller of the current, the smaller of the magnetic force. So we have current here. Okay, so we can using this one to form a switch or for switch. So when the current is bigger, too big, we can making the I part, E part, closed together. When the current is small, because the mechanical force, the E and I part separate. We can using this close, the separate, close, and separate mechanical movements to cut off or off or on, off or on a facility. Okay. So actually, this is frequently used in controlling the power distribution facilities. Okay. Automatically, we can using a CT to detect the current on the facilities. If the current is small, or too big, we can on or off the facilities by using such devices. Okay, so that's the usage of the EI type, coilers in practice. We can use the current here to control, on, off the EI parts. So hope you understand the principles of it. So our task is that here to analyze for a EI type of the circuit, magnetic circuit, how to analyze, how to analyze. Okay. So now we have a so-called domain theories to explain how the magnetic field is induced inside the core materials due to the magnetizing strength H. So we suppose that materials that contains many small invisible magnetic pole, just like the magnet we played when we was child. Okay, so many magnetic pole materials. This we call it NS magnetic poles. It is very small, invisible, but numbers is limited. For a good materials within a unit volumes, suppose there are 1,000 small poles. Small poles. For a poor materials with a unit volumes, there are just 100 small poles. These small poles interact with the external magnetizing force H. When H is weak, this H can pull 1% of the small poles align with the directions of the H. As you increase the strength of the H, more and more small poles has been aligned with the direction of the H. At the end, when the H increases to certain levels, all of the small poles be aligned with the direction of the H. After that, even in increase the strength of H continuously, no more small poles available to align with the direction of the edge. That's the saturations. Okay, saturations. So that's why there is so-called nonlinear relationship between the magnetizing force H and the produced magnetic field B. We can express the relationship between the magnetic field B induced by the H to the H as the flux density B equal to externally produced magnetic field component, that is the H at mu zero, no matter whatever condition of the materials. There is a basic magnetic field produced by the H is mu zero plus H, even in the air. Okay, this is mu zero H is the basic magnetic flux produced by a given current with H. There is additional magnetic field due to the small pores. So there are two parts. One is the fundamental parts for whatever materials they produce this one. The other one is the additional B that due to the small pores align their directions to H. How many small pores align their direction to H depends on the strength of H. Okay, so the stronger of the H, more small poles align their directions to H. But the number of the M small pole is limited. Okay, but remember that small poles number is limited, not infinite, limited. Okay, different materials has different small poles numbers. That's domain theories. Okay, so we can finally introduce relative probabilities. Okay, so because M proportional, as I said, proportional to the H. Okay, so we can introduce additional values. Okay, so we can write into the B equal to mu times H. So the mu can be determined based on the ratios of B and H, which will be nonlinear one, because the small pole numbers is limited. At the beginning, the small pole numbers is enough to align their directions with the strength of the H. When the strength of the H is stronger, more and more small poles align their directions to the H. At the end, all of the small poles align their directions to the H. And then you increase the H. There's no more poles available, but the fundamentals one is still increase. Okay, so that's it. Okay, so therefore we have the so-called pH curves. Sorry. Okay, if you do experiments for different raw materials, you can obtain the pH curves like this. So that's the meaning of here, this. Okay, so then because the H usually proportional to the current, right? You apply. So for small current, you have a small H, and the B increase linearly with the H. Okay, so we have a linear part for the linear part. And then as the H increased, so the B no longer increased linearly. There is a nonlinear part. Okay, this is a nonlinear part. And finally, when you increase the H, that means the current further, the B no longer increase anymore. That is the saturations. Okay, that means the flux already full, okay, inside the core. The core no longer allowing more magnetic flux lines. Okay, that's the situation of it. Sometimes we use the linear parts. Sometimes we use the nonlinear characteristics. Sometimes using the saturation characteristics. So linear characteristics, nonlinear characteristics, and saturation characteristics of the pH curves for a given core materials are all useful. Depends on the usage of it. So, how to use it. You cannot say linear part is good, nonlinear part is not good, and the saturation is not good. You cannot say that. Good or not good depends on how you use it. Okay? That's the pH curve. Because that the ratio of the B over H is the permeabilities. Look at here. So for this part, the permeability is a constant. Okay? That is the biggest as constant. So permeability is mu in the linear parts. And permeability in non-linear part is becoming smaller with H increase. Okay, so you have two right things that I would like to tell you that. So the permeability, because permeability is the ratio of the B over H. In the linear part, as you see here, so the permeability is mu is a constant at large. Okay, the slope, right? Permeability is the slope in the pH curve. Okay, so linear parts is large and constant. As into the nonlinear parts, the permeabilities in nonlinear parts is becoming smaller with the age increase. Okay, it's understandable. And when it comes in the saturation parts, okay, permeabilities becomes small values. When the H increase, becomes smaller, small. Okay, so you can imagine to draw that the probabilities against the currents. At beginning, very big is a constant. The probabilities mu is a constant. And then becomes smaller. Okay. So at the linear parts, the probability is a constant and bigger. We come into the nonlinear parts, okay, the probability becomes smaller. And we come to the saturations, the probability becomes much smaller, small. When H be very big, B keeps no change, that the ratio of the BH, right, becomes bigger and smaller. That's the situations of permeability mu. Okay, so of course, if you would like to be strong magnetic field, okay, and with a relatively small current, please using the coils in the linear part. That is the high efficiency. That's the BH curve issues. Okay, it's BH curve issues. Now, another issues. That is the AD current issues. So what does it mean by AD current issues? Because that in the core materials, if you have small pores, then surrounding each of the pores, they induce currents. Okay, if you all the pores are not in one direction. For example, if you have a domain, if we have a piece of a piece of the core materials, then you have many small poles. So each pole has directions. For example, each pole has directions like this. Pole. So each pole generate a small current ring. You also has inside the pole okay. Okay. Now, mu is the ratio of B over H. The B is not zero, therefore, it is impossible, okay, the mu is zero. Okay, so mu is the B over H. B over H. Okay. Okay, so can you see that the small rings? So for each of the pole, magnetic pole corresponding a small current ring, small current ring. Imagine that in a small part of the course, if we have a small ring that have the directions in the counterclockwise directions of the current small ring, okay, small ring, and these rings touch together to each other. So if all these rings, okay, touch together and align with the magnetic field H, okay, then we have many small rings like this, and each ring has a counterclockwise small ring of currents. Inside, in the center part, the adjacent rings cancel their current. For example, for these parts, so the upper goes to left, the lower goes to right. For next ring, the upper goes to left, the lower goes to right. So left, right in this part cancelled. And what left is upper and lower. So at the end, look at here, at the end in the edge, in the edge part, you may have an effective current. Okay, so there are so many small rings, right? Current. So each of the small poles actually contributing to a small ring of current inside the core materials. Okay, in the central part, the small core materials may be the small poles current may be cancelled with each other, but at the AD part and the edge of the piece of the coils, there are some current like this. So AD currents. So these AD currents together with the resistance of core materials causes some energy losses. Okay, that's the AD current losses. Okay, so that's why in some transformers, when you're using a large current to go through transformers, the core materials become very hot. Okay, making the materials hot. So there is a so-called core losses. Okay, the core losses, one of it is the AD current loss, which is due to this effect. Okay, so you can imagine that. Okay, there are many small poles. It doesn't matter actually because this is just a theory, but in practice we need to carry out experiments to record the energy losses, okay, in practice. So this slide actually tries to explain to you two new concepts. One is the pH curve issues. In practice, we use the current, and induced voltage to get the pH curves. From the pH curves, we experimentally to find out the permeabilities of a given materials as a function of the current I. So permeabilities as a function of the current I, which is used to estimate the inductance of a given coils in practice. Because it is changing with current. We can use it in a linear parts, which is a constant. We can use it in the nonlinear parts, which is a non-constant. Okay. And the second one is that when you have the core materials used in coils, there are energy losses. So these energy losses, one is eddy current losses. Okay. The other one is the hysteresis losses. So in addition to the eddy current losses, we have one more losses, that is the hysteresis lobe losses. What happened to it? Looking at these diagrams, if this is a new materials, and at the beginning, there is no magnetic flux produced because you have no current applied. So if you write the current be zero, the magnetic field in it be zero. Then we will increase the current, or we say magnetic force, or we say the magnetizing strength H. They are proportional to each other. Then the magnetic field increase with the increase of the currents. This is the increment of it, increase. So with the H increase, the B increase. So this is at the beginning, as the fresh materials, you can apply some of the currents, then change the currents, magnetic field strength increase at this moment. Okay, among this magnetic field B, part of it is because the internal magnetizing process. That's the A. That's the A. This is the total B. This is the additional one, A. Okay? That's good. However, if you again to reduce the currents, theoretically, when the current reduced, the magnetic field reduced too. But some of the small poles does not change their directions immediately. They keep their directions there for a while. So when you reduce the current, the magnetic field not reduce as the same as it increased. So this is the increased process. When you reduce the currents, so you reduce currents, the magnetic field reduced, but not follow the increasing path, not follow this path. When the current be zero, they still have magnetic field remain in the core materials. That is residual flux. Okay, residual flux. So when the current equal to zero, they still have magnetic field remain in the core materials. That's the residual flux. When you further making the current reverse their directions and to certain values, then the magnetic field becomes zero inside the core. When you increase the current in opposite directions further, the magnetic field will increase to certain values. Similarly, when you reduce the current in opposite directions, the reducing of the magnetic field no longer follow the original increasing path. they follow in a different path, as shown here. When the current to zero, the magnetic field in opposite directions remains non-zero. So there is a magnetic field in opposite direction inside the core materials, which opposite to these points here. And when you increase the current to opposite direction, the magnetic field finally gets to zero. When you further increase the currents, the magnetic field will increase, follow a different path to the maximum values B. And when you reduce the current again, the magnetic field will change like this, which occurs for the AC current. So because the AC current change their values and directions periodically, as a result, the magnetic field inside the core that carrying a AC current change their magnetic strengths, in a way like this loop. Current maximum positive, right? Zero, zero, the maximum is negative, when the zero current be zero, current be zero. And when the magnetic field be zero, the current non-zero, when the current be maximum, magnetic field be maximum. When the current decreases, that when the current right to zero, magnetic field not zero. When the current to opposite directions to certain values, magnetic field zero. When the current to increase and opposite direction to maximum, magnetic field maximum. Then the current reduced to zero, magnetic field non-zero. When the current reduced to the positive values at certain values, magnetic field zero. When the current increased to maximum values and a positive polarity, the magnetic field be the positive, right, maximum. So this is the hysteresis loop. Hysteresis loop. So this hysteresis loop has an area. So the area is the product of the B and the H, or the products of the phi and F, or the products of the I and V. So there is a energy loss. This energy loss can represented by the areas of these BH curves. So the energy losses here in practice can be simply represented by the BH, the BH areas here, delta BH area here, the VI. So that's why in practice the BH is the energy representatives, VI energy representatives, B square representatives, H square representatives, V square, I square, or even the phi and A. They all is the symbols of the energy. Symbols of energy. B, H, B, F, B, I, and so on. Because proportional to each other. So as a result, the core losses includes two parts: AD current loss and hysteresis losses. Now, you should understand, using a coilus, you have three types of energy losses. One, resistive losses. Okay, so in practice, on coilers, there are two types of energy losses. One is the resistive energy losses, R. The other one is the core losses. The core losses, because the AD current losses, hysteresis losses. And in practice, the core losses can be represented by using a equivalent core resistance. That is the equivalent core resistance, because the resistance represents energy losses. Okay, core equivalent resistance, which we will study in details when we are using the AC and transformers. Okay, so that's the end of today's lectures. So hope that you have good understanding of the magnetic circuit, particularly about the properties of the magnetic materials and the possible drawings of the magnetic circuit for a given coilers. In next Tuesday, we have tutorial sessions on the magnetic materials called coilers analysis. And please pay attention to that. After lectures, the assignment 1 is available on Blackboard. Okay, so you can log in the Blackboard, download the assignment, and try your best to answer all the questions in the papers of the assignment, and submit 1 PDF files onto the Blackboard, through the assignment link by the midnight of 20th, 20th of the October. That is the end of the next Tuesday. End of next Tuesday after the tutorial sessions. Okay, so we give you a longer time because that you need time to review and learn, and review and learn and try your best to complete the assignment 1. So it serves as a self checking and learning and a revision exercise. Okay, so that's the end of today's lectures.